All right, let's take a look at a problem from section 2.8. We're dealing with the discontinuity of f of x equals the cosecant of x. Now, f of x equals the cosecant of x is a reciprocal function. It can also be written as 1 over the sine of x. Now, what that means is that the discontinuities for the cosecant of x are the positions where the sine of x equals 0. So let's take a look at the graph and sketch the sine of x and see where that equals 0. So as we would sketch it, we would want to go 2 periods to the right, 2 periods to the left. We're graphing our sine function. Starts at the horizontal, goes up to a maximum, back to a horizontal, down to a minimum, starts over the period. After a period of 2 pi or a horizontal distance of 2 pi, it continues that pattern as a periodic function. It is a sinusoid, the graph of the sine of x. So here we have 2 periods of the sine of x. So we're asking where is the cosecant discontinuous. So that happens everywhere the sine of x crosses the x-axis, because remember, sine of x is in the denominator of the cosecant. We cannot have 0 in the denominator of the cosecant. Now what that means graphically is where that sine x equals 0, we have asymptotes for that cosecant function. Now I didn't put the labels on the axes here, but we're out here at 2 pi, here we're at pi, half the period length. So if you take a look at this graph, the cosecant function would be the horseshoe shapes that are contained by these vertical asymptotes. The cosecant function piggybacks right on top of or below the sine function. These relative maximums for the sine function become relative minimums for the cosecant function. But this question in particular is asking where is the cosecant function discontinuous? In other words, where is it undefined? It's the same question as asking for the equation for the asymptotes of the cosecant function. So you can see that the first positive asymptote for the cosecant function is at pi. So I would say, well, x equals pi, and for the cosecant function, the asymptotes are at every half period length away from one another. So if I have one at pi and the period is 2 pi, that means I jump a distance of pi to the right or pi to the left, I'm back to an asymptote. So that means that my equation is x equals pi plus pi times k. Okay, and if we're going to bring a variable in, we better say where k comes from. K is a member of the integer set. And in this case, because we're adding pi times k to pi, we can make that a little more succinct and just say x equals pi times k. Those are all of the positions that the cosecant function is discontinuous. The cosecant function is discontinuous at every asymptote. Here's an equation for all of the asymptotes of the cosecant function. And again, this is where the cosecant function is discontinuous. Now, if you notice, it's an asymptote at every one of the graphs. And in this case, because the behavior is different at each one of the graphs, we would call those odd asymptotes. So the cosecant function has odd asymptotes, and at each odd asymptote, it is discontinuous, which means that the double side limit does not exist, and in this case, that is a vertical asymptote. All right.